Hello everyone, welcome back to Alkaline Hydroxide 784, and today in the physics series, oh by the way I'm so sorry about the late episode, never mind, it's a long story. But anyway, today we will be looking at a new topic, and I've already opened up my Google because I definitely do not remember how to define magnetic flux in the Weber, so yeah, sorry. Okay, but I know what it is, just that I'm very bad at that particular definition. So let's just get right into it. So, what is magnetic flux? Well, we know what is magnetic flux density, and we know that it's related to the magnetic field. So, the idea of magnetic flux is that it's the measurement of the field. So, yeah, but we are looking at how much in a certain area is there. But instead of looking at it over the area, we're looking at the overall the total amount of it in that area. That is why you don't call this density but the actual flux, like the total magnetic field passing through that area. And yeah, that's what magnetic flux is. So now we will go to the Weber, which is an even more confusing way, an even more annoying definition to write because you have to remember all the SI units and all the other things that you have to say. So you can just go and search it online. You should get a generally detailed explanation of Weber. So the Weber, which is the unit of magnetic flux, which is an SI unit kind of, it is one Weber is the amount of magnetic flux linking an electrical circuit of one loop of wire, like one turn, produces an electromotive force of 1 volt and in 1 second, kind of, as the flux decreases to zero. And remember, okay, so but if you want to look at it in terms of the area thing, right, you can say it as 1 Newton times, like, over an area of 1 meter square. So you just use the SI units and just do that. You don't need to say the 1 second part. Talk about the 1 Newton and 1 meter part, 1 meter square part. So yeah, let's just look at your school notes for that because I honestly do not remember how to write the exact so-called correct definition here. So yeah, just remember that Weber is the unit for magnetic flux and use and hope that you don't have to answer the question on defining those two things. Unless you're really good at memorizing stuff, then I suppose you can. Okay, so the next learning outcome is recall and solve problems using the symbol for magnetic flux equals to BA. Yeah. Okay, so magnetic flux is a little bit different from magnetic flux linkage. We will get to that in a few seconds time. But magnetic flux itself is equals to the magnetic flux density times the area that you're looking at. So that's pretty much it. Just if you're asked to find out the magnetic flux, so this is once again a reminder to read all the questions carefully. Do not forget to read the question carefully. Make sure you're finding the right thing. Yeah, so magnetic flux is B times A, and when you look at it, you must make sure that it's perpendicular. Oh yeah, that's important to look at the perpendicular thing. Don't just anyhow do it. Yeah. So if you want to be a bit more, like if you're a bit more encompassing, you can use the cosine theta, but I think magnetic flux itself. But if it would make more sense to look at the perpendicular magnetic flux density times the area that is passing through, the perpendicular area that the magnetic flux density is passing through. Yes, that makes sense. So now we will go on to magnetic flux linkage. The magnetic flux linkage is equals to the magnetic flux going through the number of loops, like a certain number of loops, perpendicular to the loop basically. Yeah, in other words, magnetic flux linkage is equals to n, which is equivalent to the number of loops, BA times cosine theta, which is more important if you're looking at the perpendicular part of it. because when you're looking at the bee passing through the loop, you would want it to, actually go perpendicular to the area in order for the linkage to work. So yeah, okay. So cosine theta in this scenario, I'm not sure. Wait, cosine theta. I think it's like the angle between the. Okay, but you get the idea. So the area is like, if you imagine the coil, right? Like if you have a coil, the area is that the cross sectional area there, not this way, like not the horizontal, but the. I think you'll get it from what I draw there. Yeah. So that's the magnetic flux linkage. So now we'll go to the stuff that I can actually kind of explain. So infer from appropriate experiments on electromagnetic induction. Okay, so right. So first of all, the first point that we need to prove that is that the changing magnetic flux can induce an EMF. So how do you prove that? Well, you can first have a coil and you connect it to a voltmeter or some whatever can measure EMF, and that will change the EMF, like that will induce an EMF whenever you move the magnet in and out. If the magnet stays in one place, there will be no EMF, but once you start moving the magnet in and out, it will change the magnetic flux, because as the magnet moves closer or further away, the magnetic flux linkage changes, and the strength of, like basically the strength of the field, or in other words the magnetic flux density changes, and this actually means a changing magnetic flux, and this induces an EMF. And you might be wondering why it induces an EMF inside the coil. And that's because we saw in the last episode that, you know, like the electromagnetic connection in a sense. Yeah, so anyways. So this is basically the phenomenon of electromagnetic induction. So you're using a magnetic field to induce an electric field inside a conductor. So the magnetic field kind of attracts the internal stuff like the electrons and things like that, and it creates a current in a way. But anyways, so now you look at the next point. What is the direction of the induced EMF? So when you induce the EMF, it is suddenly like you suddenly induce something, and this coil was originally not having an EMF. Like there's no battery or anything forcing a current through it. So the natural response would be to go back to the state that it was originally at. It would want to go back to not having an EMF. So in order to do that, it would want to oppose the force that created the EMF. So the direction of the EMF would in turn create a magnetic force that opposes the magnetic force that created the EMF to begin with. If you're very confused at this point, sorry. But yeah, that's just how it is. So let's imagine if you have a magnet and you're shoving it towards the coil. The coil obviously wants to not be charged in a way. So it will create an EMF that would in turn attempt to repel the magnet away. So that would eventually decrease the change in the EMF. You know what I mean? Like, and the more that opposes it, the less the change in EMF. And eventually there won't be any more change in a sense. So the idea is that if like this will be easier seen with the coil and the magnet example, because you can do the right hand rule and then see which side is north and south. So if you're shoving the north end of the magnet towards the coil, the coil will want to repel the end of the magnet. So it would in turn create a north pole in the direction of the magnet and a south pole on the other side, and that will repel the magnet. Yeah, so but if you're removing a magnet, if like the magnet was originally inside the coil and you're pulling it out, the coil will want to attract the magnet now because it wants to remove its EMF. So in order to attract the magnet and the north end is facing the coil, right? The coil will then create a south pole facing the north pole of the magnet so that it can attract the magnet. And this will eventually balance out the whole EMF situation. Yeah. So that's the idea here. And the last one is that what affects the magnitude of the EMF. Okay, so the EMF is the magnitude of the EMF is equals to the change in time of magnetic flux linkage. So in other words, the magnitude, so you're looking at absolute value, not the negative positive part, but absolute value would be equals to the NBA cosine theta, the change in that, over T basically. Yeah, so if you want to get the actual actual EMF, you will put a negative sign in front. That's basically how it works. Yeah. Because of the opposite thing, so opposite means you put negative in front. But if you're looking at absolute value, it's just d this thing or dt. Yeah. So right, so the last one is explain simple applications of electromagnetic induction. No, sorry. Before that, recall and solve problems using Faraday's law of electromagnetic induction and Lenz's law. Okay, so the Faraday's law of electromagnetic induction is about the magnitude. So the magnitude of the induced EMF is equals to the change, the rate of change of the magnetic flux linkage. And Lenz's law is about the part where the induced EMF opposes the change producing it. So that's pretty much what they are. And when you do your problems, you just need to remember those two and then write the right equation. And you'll be good. You're fine. Just if you're looking at a certain context, like for example, the one that they use usually is this square coil, or not a square coil, you have two parallel wires and like a square coil, and there's one straight metal conductor moving towards the right, that situation. So from there you can, if you know how to apply these laws and then use your left or right hand to figure out where everything is going, then you will be able to solve the problem in a sense. And yeah, I guess it's easier to draw it out. So for example, if the conductor is going towards the right and the magnetic field is acting in this certain direction, then the force, the induced EMF would want to create a force that pushes it back to the left. So you must think about what way the current will go or what way the EMF will go to produce a force that pushes it back to the left. So that's the idea. So yeah, so now we'll go on to a very famous example, because the last one is about simple applications, but I think I'll just cover one famous one, which is electromagnetic induction can be found in, well, alternating current in a sense. Yeah, so to create electricity, you would be having a thing that turns around, like a coil that turns around. And when you're turning the coil around, right, if you put two magnets on the side, if you didn't take into account, if you just let it turn without thinking about anything else, it would eventually stop because the coil cannot keep going in one single direction unless the magnetic poles are reversed. And that's why in alternating current they kind of reverse the polarities every half turn, and it kind of allows the thing to keep turning and turning instead of stopping in one place. So that's pretty important. But if you're looking at other applications of this, you can look at stuff like speakers or you know many other things, I suppose. You can just look online. There's a lot of examples, and I hope you find them interesting enough. Yeah, those, or if they just ask you how to explain this, they give you a system and maybe, not sure if a doorbell is involved in that, but okay, they give you a system like that, you can just explain it using your knowledge of electromagnetic induction. It shouldn't be too hard to explain, so don't worry too much about it. Okay, so yeah, that's about it. Yay! So if you found this video useful, or if you can press the like button and subscribe. But if you want me to talk about more things, please do comment below so that I can attempt to actually do some research and find something to talk about. If you do not want me to do that, then it's okay, doesn't matter. Yeah, so with that, I would like to say thank you and bye!